Hi friends, so welcome to lecture 57 on my helicopter dynamics course, and today we are going to look at the flap equation in the non-rotating frame. Specifically, we are going to find the eigenvalues of the flap equation once they have been transformed into the non-rotating frame. I'm Dr. Ranjan Ganguly. Now we showed in the previous lecture that you could transform the flap equation into the non-rotating frame using a mathematical tool known as the Fourier coordinate transformation, or the FCT. Now once we had done this transformation, you obtain the non-rotating frame equation. So you essentially have four equations. You have one equation in beta 0, one equation in beta nc, another in beta ns, and then there is an equation in beta n by 2. Now the interesting thing is that the second and third equations, they have some coupling. So essentially you will see that beta nc and beta ns are coupled in these two equations. However, the first and fourth equations have no coupling, so these are equations purely in terms of beta 0 and beta n by 2. Now what's this n? This n is actually not like a summation in a Fourier series. It's a constant value and it depends on the number of blades. So we can define this small n as 1 to capital N by capital N minus 1 by 2 for n odd, and small n is 1 to capital N minus 2 by 2 for n even. So let's take two cases to illustrate this situation. For example, if we have a four-bladed rotor, capital N would be 4. So we go here to the even value, we plug in 4 here, we get 4 minus 2 by 2, that is small n is 1. The second case could be a three-bladed rotor, capital N would be 3. So we go to the first definition here because now capital N is odd. So 3 minus 1 by 2 would be 1. So these are the two typical cases. Of course, if you had a 5-bladed rotor, 6-bladed rotor and all, more number of values of n would be there. So let us look at the case of a 4-bladed rotor for concreteness. So here small n equals 1. Now to find the nature of that particular differential equation, we said beta psi is beta into Es psi, where S is the eigenvalue in the fixed frame. Now when we substitute this into the four equations I showed before, the first and fourth equations are going to turn out to be similar to the rotating frame equation, because if you take a look at them, they are very similar to the rotating frame equation. They have a beta double star term, they have a gamma by 8 beta star term, and then they have the nu beta square beta term. However, for the second and third equation, these equations will be different. So therefore, if we look at the beta 0 and beta n by 2, the non-rotating values are going to be same as the rotating eigenvalues. So if you want to put it mathematically, for beta 0 and beta n by 2, S equals to SR, where SR was what we obtained in the previous lecture for the rotating equation for each blade. Remember, that was a complex conjugate pair. Now we take the second and third equation and we write it in a matrix form. So this clearly brings out the coupling terms, which you can see here in terms of beta nc and beta ns, and these are the diagonal terms. Now essentially this determinant should be 0, and therefore we can write this equation here. The determinant should be 0 because we want a non-trivial solution in terms of beta nc and beta ns. So this is the equation we get, this into this minus this into this. So that becomes a plus here. So that's the equation. We can solve it, and if we solve it, we get this particular solution. So S is minus gamma by 16 plus minus I root nu beta square minus gamma by 16 square plus minus in. So if you recall from our previous lecture, the term here involving the gamma and nu beta is essentially same as SR. Okay, so we can write this S as SR plus minus IN, and these are going to be the eigenvalues for the second and third equations, which involve beta NC and beta NS. Now we can see that in all the cases anyway, the real S is equal to the real part of SR, and even in this case of the second and third equation, that particular fact holds, that real S is equal to real SR. And the exponential decay rate is the same in the fixed frame and the rotating frame. This is very interesting fact, that the decay rate does not change between the fixed frame and the rotating frame. So what of course changes is the frequency, and we will look at that later. Now let's go back to the equation. So we have got the eigenvalue, and now let's take one of the equations, say the third equation, and we can actually write beta nc by beta ns in this form. And if we were to go and substitute the eigenvalue in this equation, we would essentially obtain the eigenvector or the corresponding mode shape. And if we do that, we can show that beta nc by beta ns is plus minus I, which is equal to plus e to the power plus minus I into pi by 2. So these are the eigenvectors for the problem. Now this tells us something interesting. It tells us that beta nc leads beta ns by pi by 2. So now if we look at the eigenvalues corresponding to this second and third equation, we will see there are two clear cases. One case corresponds to the high frequency mode, that is the SR plus IN root. The second case corresponds to the low frequency mode, that is the SR minus IN root. But these cases are a little bit complicated because it depends on the value of nu beta and gamma. Specifically, you are going to get a different result for a hingeless rotor and an articulated rotor, because the nu beta value in some cases is going to be very close to 1, and in some cases is going to be quite further from 1, and that is going to lead to different situation in terms of the complex roots. So we are going to then land up with a high frequency mode and a low frequency mode, and also a progressive mode and a regressive mode. And in the next lecture I'm going to show this for different types of rotor, and we are going to look at a specific case of four-bladed rotor and investigate this aspect further. So I will end this video here. I will see you in my next lecture.